So, again, we're going to start off with a little game. I want to make sure everybody is caught up. First, you're going to take your age, and then you're going to double it, then you're going to add 1, then you're going to square it, then you subtract 1, then you divide by 4, and then whatever the result is, you subtract your age from that. Okay. So, I hope everyone's with me. Now, tell me the number. I need a volunteer. 484. You are 22 years old. I need another volunteer. Yes, for sure. Sorry? 324. Young one. You are 18 years old. Need another volunteer. Rian? 529. Sec. Oh, okay. Yeah, you're 23. You keep doing this, I'll take another volunteer. Any more willing volunteers? Nafisa, are you a willing volunteer? No? Okay. Jose, are you a willing volunteer? Oh, okay. At 324. Already covered. Okay. Let's see, Edgar, are you a willing volunteer? Okay. Already. Ashanti, are you a willing volunteer? So, what? Oh, okay. Alright, we got a couple of repeats. Okay. Willing volunteer? Okay. Anybody willing volunteer and not represented already? Annalicia? Okay. So we covered everyone already. Okay, amazing. Alright. Did you play along?
Yeah, I'm still working.
Okay. Okay. Alright. So until I get some more willing volunteers, how did I do this? Had to think about it, had to think real hard, had to use my powers of divining the secrets of the universe. And how did you figure that out? So the first time I got the answer right, everyone said, "Wow." The second time, everyone said, "Pretty good." Third time, everyone's like, "Really?" Must be a secret. Okay. And Shaquille guessed my secret. Square root? And that's exactly right. Okay. Now, what made you say square root? Ah, okay. Okay, so you guessed based on the... Alright. So, were you looking at these numbers when you guessed that it was square root? No? Okay. You're supposed to. Alright. Okay. Alright. So, she outsmarted me. One of the things, hopefully, that a person could do is to look at these numbers, and after a while you sort of start to see a relationship between these things. First of all, as soon as, who was it, Rian said 529, we all knew that his age was going to be bigger or smaller than everyone else's. We all knew it was going to be bigger. So already we guessed the relationship that the bigger the number is, the bigger the age is. So that already tells you something about what has to be going on. Okay. So that's what happened here. We made a guess based on clues and based on a pattern. That's not the only way to figure this out. We could actually do this, you could say, precisely, without guessing. Right? Because as it stands right now, if you'd said, are you just taking the square root? I could have said no, and you wouldn't know if I was right, or you wouldn't know if I was telling the truth or not. I could have said no and just kept you in the dark. But we can establish that this is exactly what's going on precisely. Okay. How are we going to do that? Well, the first thing you start with is an age. What shall I call that? Call it X. Then what do? No. Next we double it. And when you do that, what do you get? 2x. Next you add 1. And what does that give you? 2x plus 1. Next, you square it. And what does that give you? Well, the easy answer is to say it gives you 2x plus 1 squared. It gives you 2x plus 1 times 2x plus 1. So guess what we need to do? We need to figure out what that is. So if you work this out, you get 4x squared plus 4x plus 1. Now what's the next thing to do? Let's subtract 1. Now when you subtract 1, what do you get? 4x squared plus 4x. What was the next thing? Divide by 4, which will give you what? And then what was the last thing I told you to do? Subtract your age. And when you do that, what does that give you? X squared. So when you tell me that number, what do I have to do? All I have to do is take the square root, and that gives me your age back. Pretty sneaky, huh? This is a general rule, and this is always true. No guessing involved. You dig? So notice that these are two very distinct approaches to how to figure out what's going on in this little mental game. And these two different approaches have two different names when we talk about problem solving. Okay. Okay. So the first one, where we looked at a bunch of numbers and we said, gee, this looks like what's going on, that's called inductive reasoning. Inductive reasoning is when you go from a bunch of examples to try to guess the general rule. The second one that I showed you with the algebra is called deductive reasoning. In that case, you start with the general pattern and then you try to apply it to specific cases. Notice it took us a little bit just to exactly figure out what the general pattern was. But we came up with x squared. There are many ways to use a general rule. Some of these we've already talked about. For example, every day in February is a winter day. That's true. My birthday is February 28th. That's also true. So what can you conclude? My birthday's on a winter day. There you go. So these are general rules that are always true, and then you can draw a specific conclusion from that. We've done a lot of that. Okay. But now compare it to this sort of argument. Today is a summer day, we wish. Tomorrow is a summer day. So is the day after that, and 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 the day after that. Right. Conclusion: every day is a summer day. Is that conclusion true? No. So when you use inductive reasoning, you have to be careful. And this is actually a mistake that everybody has made at some point in their life, myself included, where you take a couple of examples and you say, well, it happened this time and it happened that time and it happened that time, so I bet it's always true. Of course, when you lay it in a situation like this, obviously that's not, you can't really say that. But we draw conclusions from our experiences, don't we? Okay. So let's try to use some inductive reasoning and find some patterns, and let's try to find ones that are true. Okay. So 37 times 3 is 111. That's true. 37 times 6 is 222. 37 times 9 is 333. 37 times 12 is 444. Make a guess. There you go. You didn't find it yet. Okay. 37 times 15 is 555. About 37 times 18. 37 times 21. Great, you found the pattern. Okay. Now, of course, in this case, this inductive reasoning, we're putting it in the realm of numbers and mathematics, so it seems like it should be a little more obvious, a little more reliable. Well, with arithmetic, I think we can be pretty confident. Give you another example. 1, 1, 2, 3, 5, 8, 13, 21. Can you find the pattern and guess the next number? Thanks. Okay. I want to give people a minute to ruminate on this. So for example, let's just pick a number, the number 5. Where could the number 5 come from? 2 and 3, exactly. And where does that last number 21 come from? Okay. So you're exactly right. So you found the pattern, so now we can figure out the next number. The next number is going to be 34. What about the next number? 55. 89, 144, etc., etc. So, as Daniela just said, this is a really, really famous mathematical sequence. This is called the Fibonacci sequence. So, just a quick comment about this. Next time you're outside and there's a flower that the weather has allowed to live, count the petals on each spiral. It's most obvious in a sunflower, but this works for most flowers. If you see a pine cone, count the leaves in each spiral in a pine cone. They're all numbers from a Fibonacci sequence. And not only that, if you count the numbers either in, it's not consecutive spirals, it's spirals going clockwise versus spirals going counterclockwise, you will get two different numbers from the Fibonacci sequence, and they will be consecutive numbers from the Fibonacci sequence. So I'm just going to leave you with that thought for a second. We're going to come back and study this sequence and applications later in the semester. Turns out it appears all throughout mathematics and all throughout nature. More on that later. Alright. Circles and chords. If you put points on a circle and connect them with chords, how many regions do you get? So first of all, I have to make sure that everybody knows what a chord is. Okay. Not something you play on a piano, in this case. When you draw a circle, and when I say put points on the circle, I'll put points on the edge. When you connect two edge points on a circle, that is called a chord. So that's a chord. Alright. So let's try to figure this out. What happens if you put 1 point? What happens if you put 1 point? When you connect your points, how many regions do you get? How do you get 2? There's no other point to connect it to. So how many chords are we going to draw? None. So how many regions do we have? 1 region. Okay. Points. 1 point gives you 1 region. Next. What happens if we have 2 points? Absolutely. You get 2 points is exactly one line that you can draw. Clearly this gives you 2 regions. Next. What about 3 points? Okay, so let's make it look something like this. 1, 2, 3. So here are the 3 points. How many lines, how many chords do we get to draw? 3. This one, and this one, and this one. And I think you can see fairly clearly that this gives you 4 different regions. So far so good? Okay. What about four points? Did you draw it out or are you guessing? You're guessing? Okay. So is it 8? Did you do it? Oh, okay. 2. Okay, now first of all, how many chords can we draw? Really? Exactly. There's the 4 obvious ones, and then there are 2 more obvious, and then there are 2 more obvious ones. Exactly. Okay. And you can quickly see that there are 8 regions. Awesome. So far so good, right? And what about when you have 5 points? One, 2. Now when you say 16, did you draw them already or are you guessing? You're using the pattern. Okay, good. Well, you know what? Let's do it. So, oops. Okay. Now I want to count these carefully. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Awesome. 16. Now, and we have to do it. Six points. So, how many regions do you think we're going to get? Is it 32? Let's check it out. So, oops. First we have to make sure that we draw in all the chords that we can draw in. this one, and this one, this one. Okay, I think I managed to draw that fairly clearly. Okay. Now, let's count. And please play along at home. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And if we're really careful, you can see that there's another one right there. Because notice that those three lines don't intersect at the same point, so it makes a tiny little triangle. So that is 31. Did we miss any? Is there now 31 kind of snuck in there, so is there anywhere else where number 32 could be sneaking in? Sorry? Where? Sorry? Yeah, but everything next to 31 is labeled. Is there anywhere else where you have three lines intersect? Did we miss one? Is there anywhere else where lines are intersecting but we didn't note that it was going to be a region? Where? So either we missed the region, or I'm about wrong. I may have not drawn it with my compass, but I don't know if I drew it wrong. Sorry? More what? Oh, bigger?
Yeah.
Oh, okay. Absolutely. Let's blow it up. There you go. Is there anywhere else where you have lines intersecting that could be forming another region? Nope. That's it. This breaks the pattern that we thought we found. Oh, there's a pattern. Okay, I've drawn it again for reference here. Okay. So it turns out that there is a formula for the number of regions in a circle with endpoints connected. We thought that it was just doubling every time, so 2 to the n minus 1 would be the formula for that pattern. Turns out that ain't it. It's that. Didn't see that coming, did you? So you can check it or you can just trust me. But this is again one of those cases where, how many examples did we have? We had 5 examples. After 5 examples with a pattern that's so obvious, you figure it must be right. But remember, what kind of reasoning were we using there? No, inductive, that's right. We were using inductive reasoning. But is inductive reasoning foolproof? Hardly. Now, it tends to work in very simple cases. And quite honestly, a lot of what you see, for example, in school is just very simple cases. Anytime you see a pattern in a class, you can be almost assured that that pattern is always going to hold. Otherwise, you get mad at the teacher for confusing you. Well, we are now beyond that. And in a sense, this is what problem solving is all about. Is understanding that you can't always follow the obvious pattern. There are general techniques of problem solving that we're going to talk about later. But one of the habits I want to break you of is I want you to be able to use inductive reasoning, because we use it a lot of the times with success, but it doesn't always work. So hopefully now you see that in a fun way. So to sum up, deductive reasoning versus inductive reasoning. Okay, so here's what we saw about inductive reasoning. Inductive reasoning, what's bad about it is that it doesn't always work. What's good about inductive reasoning? Sorry? It's easier to use. Absolutely. It's much easier to make a couple of examples and then see if you have a pattern. Right? So for example, think about this one. This example of inductive reasoning. We found the pattern and we were correct. What about using deductive reasoning on this? Do you see how to do it? Would that be harder? You'd have to figure out a formula. Is that easier or harder? That's harder. How much harder? In this case, it's a little bit harder. What about in this case? Finding the formula would be a lot harder. Exactly. So those are the pluses and minuses of each of these approaches. Inductive reasoning, it's easier, but it doesn't always work. Deductive reasoning always works, but it's harder.